In this video, we're going to construct, if you will, a qualitative way of looking at the energy levels and the molecular orbitals that are formed when we create a homonuclear diatomic. Now, I'll remind you that in the case of the hydrogen molecule, we could write plus or minus combinations that look something like this. Square root of 2, 1 plus or minus s of the 1s orbitals, so that would be psi 1s of A plus or minus psi 1s of B, where the plus combination is going to end up being a bonding combination and the minus combination an anti-bonding combination. We could similarly then write down the energy levels for this, and this is based on the H2 plus model, where we're going to have the energy of the 1s orbital plus a Coulomb integral that is based on the 1s orbital plus or minus the exchange integral based on that over 1 plus or minus 2 of the overlap integral based on the 1s orbitals. All right, so this would be a simple LCAO-MO approach to the hydrogen molecule using 1s orbitals, all right, just as we've drawn here. So when we summarize this, one way we can do it, and I'm going to draw with the vertical axis being energy, we can sort of ground this, this diagram that we're about to create as follows. All right, we're starting at an energy of 1s, so let's draw that in here. So here's a 1s energy for the atomic hydrogen. Now there's two hydrogens, so I'm going to have another one over here. So if you will, what I'm doing here is I'm basically cataloging the species along the horizontal axis. So this is going to be hydrogen A, and this is going to be hydrogen B. So this one is also 1s. So the way we're going to construct this diagram is to say when I mix these two 1s orbitals together to create a molecular orbital for the case of molecular hydrogen, I know that I'm going to create a plus combination that will end up with a lower energy down here. So remember that we might label this, for example, as a sigma 1s energy level. And I'm also going to create a combination with the minus sign of a higher energy orbital that I'll label sigma star 1s. And so what I have when I have the molecule, when my species is the molecule, I'm going to have, instead of the two atomic energy level orbitals here, I'm going to have two molecular orbitals. Now it is common for us to sort of draw connections here so that we say that these two molecular orbitals are basically combinations of the two atomic orbitals. So we might draw a picture that looks something like this to indicate that parentage. All right, but the whole idea here is that we're going to have one that's higher in energy, the E minus level, and one that's lower in energy, the E plus level. Now, just to sort of complete our tour here, let me also write down what we would have for our new labels for these orbitals. We might call this one 1 sigma G, and we would call this one 1 sigma U. All right, so that's how we would refer to these when we're referring to them by symmetry. In the case of hydrogen, it pretty much is, it's a pretty good description to talk about the 1s orbitals being added, although they are slightly different when you mix in the whole thing, when you mix in all of the orbitals. Now, I'll notice when we go to higher diatomics, and we're going to look at the diatomics across the first and second rows of the periodic table. We're going to be ordering these energies, and since the bonding and anti-bonding, so bonding and anti-bonding combinations are centered at the energy levels of the atomic orbitals themselves, it's going to matter, the ordering of these molecular orbitals is going to follow more or less from the ordering of the atomic orbitals. So I'll remind you that, for example, we know that E1s is less than E2s. In the hydrogen atom, just the hydrogen atom, we find that E2s and E2p are the same energy, but when we start adding electrons, it turns out that the energy of the two p's are a little bit higher. All right, similarly, we'll get E3s and so forth. So we can keep building up this way a diagram that would include the higher order the higher order diatomics. Now there's one place that we need to be aware of, and that is when we get to the point of creating the sigma 2pz versus the pi 2p x and y. And it's a legitimate question to say which one of these would we expect to be higher in energy. They come from basically orbitals that are of the same parentage, that have the same zeroth order energy, the same atomic energies. So which one of these will end up being higher? Well, it turns out, and I'm going to draw a picture here to describe this. And let me draw it, I guess, just to the right of this. Okay, so the picture I'm going to draw is going to depict how these energy levels change as we move across the periodic table. Now I'm going to start with lithium and go to beryllium, then boron, carbon, nitrogen, oxygen, and fluorine. So what I'm really intending to do is, these are really discrete steps, but I'm going to treat this, I'm going to draw it as though it's continuous just because it's easier to draw. So these vertical lines indicate the positions at which these various atoms would be. Now if I were to look at the energy level of the pi orbital that comes from 2px, and same for 2py, so I guess I should write that, it doesn't change very much as we move across these different atoms. All right, that energy level stays pretty much the same. However, it's different for the sigma that comes from 2pz. It turns out that that orbital starts off a little bit higher in energy than the pi orbital, but as we move across, it becomes lower in energy. So in effect, what happens is it begins to go down, and it crosses right about there. And at this point, when we get between nitrogen and oxygen, then this becomes lower in energy than these. All right, so this is going to affect the molecular orbital diagram that we're beginning to construct here. So let's see what this looks like. Okay, so I'm going to draw a big diagram now that includes lots of different atomic orbitals. And so what I'll want to do is down here at the very bottom, I'll place my 1s orbitals. Then a little bit higher, maybe a lot higher, 2s, and then finally higher still, I'll have my 3 2p orbitals. So this is 2p, x, y, and z. And I'm going to have, if I'm forming a homonuclear diatomic, I'm going to have atomic orbitals that are equal in energy on both sides of this. So these represent, if I'm forming the diatomic A2, this is one of the A atoms and this is the other A atom. All right, and A2 is what I'm going to draw here in the middle. All right, so now I know that the energy of the bonding combination of the 1s's is going to be a little lower in energy than the 1s orbitals, and the antibonding will be a little higher. All right, so I'll have this sort of mixing. I'm going to have a similar arrangement for the 2s orbitals. They're going to form a sigma bonding combination and a sigma antibonding combination. And I should probably now start labeling these various orbitals as sigma bonding 1s, sigma bonding 2s, sigma star antibonding 1s, and sigma star antibonding 2s. Okay, when I get to the 2p's, that's where I have to pay attention to this chart down here. All right, if I'm at atoms that are larger than nitrogen, then I'm going to have the next one be the sigma 2pz orbital. But if I'm below nitrogen, and let me draw that one, I guess, preferentially. So if I'm below nitrogen, then my pi orbitals, so this is the pi 2p x and y, they're going to be lower in energy than the sigma orbital for the 2pz. So my parentage is indicated like this. And then when we go above that, though, the sigma orbital, the sigma antibonding orbital, is always the highest. So sigma star 2pz, and we'll have pi star 2px. All right, so we'll end up with a diagram that looks something like this. The one thing that will change is that when we reach elements that are, say, higher than nitrogen, then these two will switch positions. All right, so when we draw these diagrams, it's important to know where you are relative to nitrogen. Nitrogen does have this arrangement with the pi orbitals lower than the sigma orbitals, but fluorine and oxygen have the opposite, have the sigma pz orbitals below. Now, I want to finish by giving these labels, the symmetry labels that we have been talking about. So, for example, this sigma bonding orbital would be 1 sigma g. The sigma antibonding orbital here would be 1 sigma u. Then we'll have 2 sigma g, 2 sigma u. All right, the next orbital here, and I've gotten a little crowded on this, but this is going to be the 1 pi u. Remember, bonding combinations with pi orbitals are always u. Then it will be followed by 3 sigma g. The antibonding orbital here will be 1 pi g. Antibonding is g for pi orbitals. And finally, we'll have 3 sigma u for the antibonding orbital of the sigma. So when you see these labels, the first number is going to tell you which order it is in terms of, climbing up through the possibilities of sigma or pi type orbitals. And the symmetry will tell you if it's g and it's sigma, then it's a bonding orbital. If it's u and sigma, it's an antibonding orbital, with the opposite being true for the pi orbitals. U means bonding and g means antibonding.